Hi everyone, welcome to our 11 a.m. press conference, the New Jupiter, a mid-mission report on the discoveries of NASA's Juno. Our speakers this morning are Jack Connerney from the NASA Goddard Space Flight Center, Kimberly Moore from Harvard University, Fran Bagenal from the University of Colorado Boulder, Heidi Becker from NASA's Jet Propulsion Laboratory, and Candice Hansen from the Planetary Science Institute.
Thank you. Yes, I'm standing in today for the principal investigator of the mission, Scott Bolton, Southwest Research Institute down in San Antonio. And we thought it would be good to give you an assessment of where we are today, approaching the midpoint in our prime mission. And also share with you some of the discoveries that we've already made and some of the puzzles that we've already encountered. And to let you know a little bit about what to expect for the second half of our prime mission. On the monitor here, you see an image of Jupiter, and of course we all remember the familiar bright white and dark bands. Now our orbit is a 53-day orbit that extends quite far out in the magnetosphere, and every 53 days we come around and we get very close to the planet. Most of our prime science is done when we speed from pole to pole in the course of about 2 hours. And I'll show you how that works in this animation. Fixed in space, the orbit looks like this, the white one. But if you put yourself in a frame of reference, rotating with the planet, it puts a little bit of a twist in each of our periapsis passes that come about every 53 days. Now, over the past 2.5 years or so, we've assembled almost 16 of these science passes. First 4 equally spaced, then 8, and now, as of December 21st, we'll have completed a net of 16 initial orbits. And already from that, we've learned some amazing things about the magnetic field and about the interior. In this animation, you'll see the magnetic field coming through the clouds. The red is where field lines leave the planet, where it's most red, it's most intense, and the blue where field lines enter the planet. And you see this equatorial belt stretched around the planet, kind of reminiscent of the belts and zones we see. And much of the field re-enters the planet in this enigmatic great blue spot that you just saw pass. We've also, by tracking the spacecraft, learned a lot about gravity. We originally thought that the heavy elements would be clustered together in a little ball in the center of the planet. And what we found already is that the heavy elements are spread more throughout the deep interior. And that's giving us a new perspective on the formation mechanism. We also know that the zonal winds that you see at the surface extend down thousands of kilometers into the surface. And as we complete the second half of the mission, we'll put orbits in between every one of those initial 16 and ultimately come up with a collection of a dense net of observations around the planet. Now I'll go to a still here. On the left in green, you see the initial net of 16 orbits. In the middle, in magenta, you see the next 16 that will accumulate over the next 2.5 years. And then finally, in blue, you see the entire picture. But if you look at the set in the middle, you'll see that as the orbit evolves, we get much closer to the northern hemisphere. And that's very exciting because we know now that the northern hemisphere is the hemisphere where the magnetic field is extraordinarily complex and really unlike what we've seen in any other planet. It'll also give us the opportunity to look at the dynamic phenomena in the 3D magnetosphere, the polar magnetosphere that we're exploring. We saw today at the meeting that the Aurora expands and contracts in time. We'd like to watch that and try to study it a little bit. And another interesting event coming up in the near future here and a few more perijoves. You know, Jupiter's thrown us a couple of curveballs thus far in the mission. With the microwave radiometer, we look deep down under the clouds to an atmospheric pressure of about a few hundred times the Earth's pressure. And we're trying to determine the global water abundance. Now, initially, we assumed that the upper atmosphere would be well mixed, and that was going to make the job relatively easy. But what we found in the first perijove, in fact, and in subsequent perijoves, is the atmosphere is not well mixed at all. There's a dense column of ammonia that comes up at the equator, and that's complicated the picture a little bit. So one of the twists we've thrown into the mission is we're going to reorient the spacecraft on an upcoming perijove, perijove 19. Now, Juno is a solar-powered spacecraft, and we usually keep the solar array and the comm antenna pointed at the Earth and the Sun. But on this particular perijove pass, what we're going to do is turn the spacecraft on its head, point the solar array and the comm antenna down, and go through a perijove in that attitude so that the microwave radiometer can scan east to west instead of from north to south. And this is going to give them an entirely new perspective on the microwave radiation from the planet. So even though Juno's thrown us a curveball, my teammates on the microwave radiometer are going to get up to the plate and hopefully knock this one out of the park. So it'll also give us the opportunity, as we extend our observations in this second set of observations, to look for secular variation of the magnetic field. The longer we can look, the more probable it is we can detect secular variation. Now, in the case of the Earth's field varies by a few percent every 100 years, and we measure that on Earth. It's the only planet for which we have a measurement of secular variation. At Jupiter, we're hoping to measure it directly from the second set of observations we have. So to talk more about the implications of the magnetic field, I'm going to turn it over now to my colleague on the MAG team, Kimberly Moore.
Hello. So this figure shows our best maps of Jupiter's magnetic field before and after Juno. Before Juno, the field actually resembled Earth's field, similar to how you would picture a bar magnet just tilted on its side. Now, with what we know from Juno, the field is far more complex. In particular, the field magnitude is much stronger than we first realized. I wanted to highlight a few of the really interesting features we found in our mission. First, there's the great blue spot at the equator. This is a region of the magnetic field that is very densely concentrated and strong. If you were to look at the planet, it's not actually blue, but this is the color scale we're using to represent it. There's also a large region of strongly concentrated flux in the northern hemisphere, but the field in the southern hemisphere is much simpler and lower in magnitude. We can see this better by visualizing the magnetic field with magnetic field lines, the gray lines, which show the direction and density of the field in space. As you can see, the great blue spot dominates the magnetic field lines, and much of the field enters through the northern hemisphere flux band and re-enters into the great blue spot. However, over large regions of the planet, the field is still very simple. These next views show if the magnetic field if you were to fly over the northern and southern pole. The northern pole looks very complicated, similar to the magnetic fields of Uranus and Neptune. But the South Pole still looks like a very simple bar magnet field, like Earth's field. None of the models in the literature could explain why Jupiter's magnetic field was so complicated in the northern hemisphere and so simple in the southern hemisphere. So this is exciting. It means Juno's discovered something really new about the magnetic field, and we have to scratch our heads a little and think about how we could possibly explain this. And the picture we're getting is complementing the other instruments on the mission, such as the gravity investigation. The complex magnetic field suggests that the interior of Jupiter is layered, and that particularly in the region that generates the magnetic field, the metallic hydrogen region, there's signs of the core itself dissolving into Jupiter, which is possibly causing this complex magnetic field signal we're seeing. And so this is something we really want to explore more with Jupiter, combining data from all of the different Juno investigation instruments. It's a picture that's really exciting. Looking forward to the next half of the mission, what we really want to find is if Jupiter's field changes in time, because we've already seen how much we can learn about Jupiter's magnetic field from how it looks in space, but there's lots of things to be learned from how or if it even changes in time. But we're really going to need a lot more orbits to figure that out, because Juno passes so close to Jupiter that it has limited resolution and longitude. So till the upcoming orbits, it's going to be hard to tease apart these signals in time and space. But it's something that we're really excited about, and we hope to discover any time variation. Our next speaker is Fran Bagenal, who recently gave the Van Allen lecture earlier this week.
Thank you very much. So talking of Van Allen, we are celebrating the 60th anniversary of the beginning of the U.S. space program with Explorer 1, where Van Allen carried an instrument up and detected the Earth's radiation belts. And we've been exploring this with multiple U.S. satellites and international teams looking at the radiation belts of the Earth, which appear to change very rapidly on timescales of minutes. Now, if we look on the right, you will see that we've also been looking at the radiation belts of Jupiter, first detected around the time of Explorer 1. And we can see that over 50 years, we see the radiation belts changing. We'd only by about a factor of 2 over that long period of time. Now, these radiation belts are, you can see the wiggling of the tilted magnetic field that Kimberly talked about. But you can see here that they're very static, very deeply embedded in the magnetosphere of Jupiter. And of course, Juno has been orbiting very close to the planet, pole to pole. And here you can see an orbit about to go through the radiation belts. And at the bottom, we have a plot that, in fact, Heidi Becker made that shows the energetic particles that are trapped in the magnetic field, the radiation belts. And you can see that compared with the models before Juno, some of these are much less intense than as predicted by the models. This is only at the high latitude regions. In the equator regions, it's similar, but the net result may be that with Juno, we may have a little less of a radiation dosage than we feared, and maybe this means we can last a little longer as a spacecraft. So the other thing about the radiation belts that Juno has been finding is a new radiation belt that is in very close to the planet. And these are very energetic ions, and they have an interesting, complicated history. These ions started out in the Io plasma torus close to the moon Io, sulfur and oxygen that was produced from the volcanoes of Io. They become charged, they become accelerated to high energy, they move out in the magnetosphere, and then they move back in towards the planet. And as they do that, they interact with the neutral cloud around Europa, become neutral, come flying into the atmosphere of Jupiter, where they become charged again. And so this little radiation belt that's very close to Jupiter is a complicated history that started off with volcanoes on Io. So this is a fun story that we're finding and putting together with the Juno mission. Now, as far as the Aurora are concerned, we have a very great opportunity with Juno because we fly over the poles, we look at the Aurora in the UV and the infrared, and then we measure the charged particles that are bombarding into the planet. And we measure the waves, the magnetic waves and the electric waves that are accelerating these particles into the atmosphere. Now, when we look at the Aurora with Juno, and the top right is a movie taken by the Juno UVS. Each image is about 15 minutes long, but you can see there's a lot of structure in the Aurora up there, and somewhat changing a bit with time. That's the southern hemisphere that's quite round and regular. The bottom left is the northern hemisphere, and the irregularity of the magnetic field is shown by this non-circular nature of the Aurora in the northern hemisphere. And when we look in the infrared and the UV, we see very different structures, and this is telling us something about the energy of the particles that are coming in and how they vary as they go into the atmosphere. So the processes that cause the Aurora are quite complicated. We have an idea based on Earth that there could be voltages like a battery at the bottom left here, sort of static structures that accelerate particles, positive, negative difference, charging across this voltage difference, a quasi sort of static situation. Or it could be that there are waves that are accelerating, and the electrons and the ions surf along those waves, gain energy to cause the Aurora. On the other hand, we know that there's a lot of turbulence in the magnetosphere, and maybe that is generating these waves and accelerating the particles. The bottom line is, we've had a lot of discussions about this, looking at the data, but it turns out that at Jupiter, it's more of an AC, a more variable than a DC situation, a sort of static environment. And we think the accelerations are strongly associated with a lot of turbulence in the magnetosphere. So the second half of the mission, we really hope to really explore this in some more detail and sort out and try and understand the physics of what is actually causing the particles that generate the aurora. And with that, I'll hand on to Heidi Becker, who's going to look at how Juno's engineering instruments are also doing science.
Thank you, Fran. I'm going to be talking about a special camera on Juno called the Stellar Reference Unit, or SRU, and it has a very important engineering job on Juno as a star camera, and it's what we use to navigate Juno through space and keep it in the right orbit. The first animation that I'm going to show gives you a kind of an idea of what the SRU's day job is like. It's a very sensitive camera that sees invisible light, and it takes pictures of star fields as Juno spins along through the orbit, and then it looks for bright stars that are in a special list inside its brain called a star catalog that have positions that are known very well to the SRU. And once it finds those, it uses them to figure out which way Juno is pointing. And this idea is pretty much the same way that sailors used to navigate the seas in the old days. They would look at the known stars in the sky, and given those fixed positions, they could chart their course and find their way. So Juno does the same thing. We're sailing by the stars. But it's really hard to do that engineering job on Juno because we're flying Juno through the most violent planetary radiation environment there is. So even though we had to shield the SRU more than 6 times heavier than we've shielded the radiation vault, there still are very high energy electrons in that environment that will penetrate the SRU shielding and create this static that you see in the star image. That snow that you see on the screen is something the SRU is shielded enough and smart enough to look above to find its way. But it's also actually a very important data set because those counts of those hits of the penetrating particles are what the radiation monitoring team uses as data. We use noise as data to figure out what the environment is on the outside of Juno because we're flying where nobody flew before. So this snow is actually the data set that led to the discovery that Fran told you about, that the high latitude radiation belt environment is actually quite a bit less than any of the models could have ever dreamed. So this next slide shows you a different side of what the SRU can do, a different facet of its capability. This is an image of Jupiter's ring, and it was collected during Juno's first perijove, and it was taken as Juno flew between the radiation belts and the cloud tops during a brief moment of peace. It's looking out at Jupiter's ring, and this is the first time Jupiter's ring has ever been imaged from the inside of it looking out. So it got to achieve a science first, and it left its own special artistic imprint by showing you a very recognizable star field. You can see the constellation of Orion in this image, and the 3 bright stars at the bottom right are Orion's belt. So once we started to get a sense of what else the SRU could do as a low-light camera, my team and I kind of got addicted and kept asking the question, what else can this camera bring back that's new, that's never been seen before, or that's never been seen in the way that only the SRU can see it? And so the rest of my talk is about some of the answers to those questions. And now that we're in the second half of the mission, because we have this longer 53-day orbit, longer than what we'd originally planned, we're now approaching Jupiter from the dark side. So this is an amazing opportunity to see things under a low light condition that otherwise wouldn't have been possible. And this is one of the images that we took with the SRU coming in from the dark side. This is another image of Jupiter's ring, but it's collected from a very different perspective. We're at very high latitude, 55 degrees north latitude, and the image was collected just as we got inside of Jupiter's ring. And we can see a lot of amazing structure in this image from that vantage point. The bright band is the main ring of Jupiter's ring system. To the right is the halo, to the left is the halo, and to the right are the two gossamer rings. And the reason that the upper part of the image is dark is because Jupiter's shadow is being cast across the ring. So this is a view that the SRU could only see coming in from the dark side. And this is an image of the dark side of Jupiter. It was collected during Perigove 11. And when we first saw this image, we thought, did our data get mixed up with Juno Cam's? Because it's got so much detail. It looks like a black and white Juno Cam image. But no, this is an SRU image, and it's extremely high resolution. We were only 66,000 miles from the cloud tops when we took the picture. And the next slide gives you a context view of where we were and how much of Jupiter the SRU can see. It's a 16 degree by 16 degree field of view camera, so we can see a lot, and we're getting very up close and personal with Jupiter. And the reason that you can see clouds on the dark side is because moonlight from Jupiter's moon Io was casting its moonlight onto the cloud tops, and we set up the image so that we could get a chance to see that cloud structure, because the other thing we were trying to see, and it worked out, was Jupiter's lightning. And the two bright dots that are towards the right of the image are flashes from Jupiter's lightning storms. And this is the closest view of lightning that any imager has ever had in all of the missions that have seen lightning on Jupiter. And one of the extra added bonuses of doing this with the SRU is that the SRU is looking at the same part of Jupiter that the microwave radiometer is looking at with its antenna 1 beam. And we've recently learned that the microwave radiometer is also a very good lightning detector, only it's looking at it in radio emission as opposed to visible light. So Juno has a great opportunity to look at Jupiter's lightning at different ends of the spectrum, and this is something that we're really anxious to start looking at with these two data sets. And the last image I'll show has something else in it, and that's Jupiter's Aurora. What you see in the lower right part of the image is the main auroral oval in the north, Jupiter, and this is another first. This is the closest view of Jupiter's aurora that has ever been made by a visible camera. It's an amazing complement to what Juno was already bringing back in the ultraviolet and the infrared. And again, we're seeing amazing structure because of the high resolution of the camera and Juno's close flight towards the planet. And you also see another lightning flash, which is the small bright dot in the lower right. And there's something else in the image again. All of the little dots and squiggles that you see in the majority of the image towards the top are relativistic electrons that are coming from polar beams, so for Jupiter's poles. So the SRU was doing 3 kinds of science when it took this picture. And it's really exciting to see what we can get out of an engineering camera. And we're really erasing all the boundaries between who or what can make a contribution to engineering or science or art. And with that in mind, I will turn it over to Candy, who will talk to you about Juno Cam.
Thank you, Heidi. So I'll be giving an update on Juno Cam. That's our outreach camera. Its primary purpose on the spacecraft was to give the public a way to actually participate in one of our missions. And so there is no imaging team per se. All of our processing is done by amateurs, and so I'll always credit the person who did the processing for these images. And they really are sort of between science and art, I think. We're almost halfway through the mission, and the camera's doing great, even though that wasn't a requirement for the camera to live more than 8 orbits. We're doing fine. No sign of any radiation damage. And Juno Cam has acquired almost 16,000 images since Jupiter orbit insertion. The outreach part of the experiment is going great. We have had over 10 million hits on the website and thousands of contributions from amateurs uploaded onto the website. But what I'm going to talk about, I'm going to pick up from Heidi's theme of the science that's getting done with this outreach camera. And so I'm just going to touch on a couple of topics, not go into great detail. This is a view of the North Pole. It's a recent image. And as we get closer in the north, the way Jack showed in the animation, we spend less time over the North Pole. It's also winter in the north, so the pole is in polar night. So we only see a handful of the circumpolar cyclones. There's 8 at the north in any given flyby. Going to the south, however, because it's southern summer, the pole is well illuminated, and in this image on the right, you can see 4 of the 5 circumpolar cyclones plus the one in the middle. The science that we're getting now is looking at the long-term stability of this configuration. We were surprised to find these circumpolar cyclones there at all. And then we didn't know, well, how stable are they? Are they going to even be there on the next Perijove pass? I can report all 8 are still there in the north, all 5 are still there in the south, plus the 2 in the center. We're looking at things like the way the center cyclones oscillate around the pole. They're not precisely at the pole. So there's, we're looking at rotation rates and so on. And I'll just mention, these cyclones are like twice the size of Texas. So they're really big structures. The image on the left is the same image, but on the right we've flattened out, and by we I mean Bjorn Johnson, taken out the difference just in the lighting from the day side to the night side. Ordinarily, the image looks like this. And this is one of the few that I will show that is actually fairly true color, what you might see if you were riding along on Juno. Most of our products are enhanced color because Jupiter tends to be a little on the pastel side. So here, for example, and this is another one of the science topics that we're working on right now. This is a view of the, looking down on the North Pole. This was taken, this is a mosaic of images that were taken as the spacecraft was inbound, coming in from the night side. And it turns out that that's a wonderful illumination angle. The lighting is really good for seeing these high altitude hazes. So now we're trying to understand the structure of these hazes, the particle sizes, why they form, and so on. This is just one of my favorites, just because it's so beautiful. But what I wanted to show you are these small, bright white clouds down here. We call them pop-up storms because we're really not sure of the process by which they originate. But there are things I can tell you. They're 25 to 50 kilometers wide. They are elevated above the main cloud deck by about 25 kilometers. When the lighting is right, we can see them casting little shadows. And even though they look really tiny on the screen, Jupiter's large, and these are all about, each one is about the size of the island of Kauai, to give you a sense of scale. But what's forming them? They seem to form along pressure ridges. Are they squall lines? Those are the types of things we're investigating with our little outreach camera. Another interesting thing is the collaboration between the project and the amateur astronomy community. And I'm going to point out 2 things on this cylindrical map. This is a map of the images that we acquired with Juno Cam on Perijove 9. And so there's a high resolution swath that goes along here, but then everything else is the low resolution that we captured either inbound or outbound. I want to point out this little SEB barge, the South Equatorial Belt barge. Just kind of park that in your mind because I'm going to show you a picture of that in a minute, a high-resolution picture. What I want to talk about is this atmospheric feature here that's to the left of the great red spot. So there's the Great Red Spot. This is what's called the South Tropical Disturbance. And there was an episode from 1901 to 1939 where the South Tropical Disturbance just stayed and stayed and stayed, and it lapped the Great Red Spot 8 times, and then it went away. And since then, it's come back roughly about once a decade. And so this was the first discovery of the eruption of this decade, I suppose. But the important thing to the project is that whenever the South Tropical Disturbance erupts close in proximity to the Great Red Spot, it affects the drift rate of the Great Red Spot. And so the amateur astronomy community got in touch with us, and because they knew we were thinking about swapping our longitudes so that we'd fly over the Great Red Spot on Perijove 18, which is coming up in February. And they said, well, we're not sure if the Great Red Spot's going to be where you think it's going to be because of this change in the drift rate. And so they recommended that we held off on the decision for quite a number of months. In fact, we only just decided about a month or two ago to go ahead with that swap because everybody wanted the Great Red Spot to sort of settle down and be in its normal speed and predictable. And so in the end, we are predicting that we will fly over it. Perijove 18 next February. Mark your calendars. Here's the South Tropical Disturbance approaching the Great Red Spot. This was in January of this year. This image was provided by amateur astronomer Christopher Go, and we have a place on our website where we have the amateur astronomers posting their images for us to use for these planning purposes. On Perijove 12, we didn't fly exactly over the Great Red Spot, but we flew close enough to it that we were able to get this series of images. And I'm going to show you this one now, which is our closest in image. And the South Tropical Disturbance at this point in time, and this was taken in April, has now passed the Great Red Spot, just past the Great Red Spot. So it's all this turbulence in here from the disturbance. And what I want to point out is how it's actually pulling strands of orange haze off of the Great Red Spot with its turbulence. Switching gears again, our first year, it seemed like everyone was in love with the anticyclonic white ovals, and that's what all of our contributions, our artistic friends and contributors. But this year it's been the brown barges. So this is the year of the brown barges. We got a nice picture of the north-north temperate belt brown barge here. These are well-known features in Jupiter's atmosphere, but these are close-ups that we haven't seen before. Here's that south equatorial belt barge. The Great Red Spot, you know, goes this way. This one rotates the other direction. And as I showed you in that map, it's quite a bit smaller, but it looks quite similar anyway. And this is a close-up of that south equatorial belt barge, and we're seeing quite a bit of structure here in the interior. So I have a feeling this is going to turn into a science topic in the next year. The next thing I'm going to do is, the last thing I'm going to do is show you a flyover movie that is basically put together from 21 Juno Cam images. So we start at the north, and as I said, it's fairly dark. We're quite close. I love this band of turbulent clouds here. As we get closer and closer and closer, you can see that the spacecraft is going faster relative to Jupiter. It's going about 129,000 miles an hour. Now watch for the dolphin. It's just after the South Tropical Zone. We just passed it. Keep your eyes peeled. See it? There it is, swimming above the clouds, splashing in the waves. And then because of the more southerly orientation of the orbit, we spend quite a bit of time looking at the South Pole as the spacecraft recedes from the planet. And again, the circumpolar cyclones come into view here, and we're able to make time-lapse sequences out of them. Jack, back
Great.
to you. Or, okay.
Oh, are you, okay, we'll now open it up to questions from reporters in the room. If you could please state your name and affiliation.
Sid Perkins, freelance. One of the presentations showed the close-up that had the auroral oval down in the lower right hand. Since it's so very difficult to figure out scales of space and distance, do you have an estimate of how wide that auroral oval was? I mean, it had to have been huge and much bigger than ours, but I was just curious if you had an estimate of width in terms of
Ooh, that's a good
tens
measure?
or hundreds
No,
of
we don't.
kilometers or?
Well, let me tell you a little bit about the general scale of the auroral oval. The auroral oval, if you imagine that picture that I showed, in fact, maybe I could, would it be worth going quickly to show you that? Maybe it's worth doing that, yeah. So we're just going to zip right back through these. Were you thinking of this one here, the high resolution one?
Yes,
That one?
down in the
Yeah.
lower right there.
Okay,
That's
so this
the
is-
band of brightness.
Right. So the exact scale of this fine structure is not so clear, but let me point out over on the left, which is the sort of schematic of what the general auroral oval sort of size is. On that size, the Earth would be smaller than that box, right? So there's probably about 5 Earths across to span the size of the auroral oval, right? Whole Earth, it's not the auroral oval, which of course is, Earth's auroral oval is tiny by comparison. It would be probably, it's hard to sort of draw, but you know, not too much. The auroral oval of the Earth would be sort of the size of this dot, so pretty tiny. So these are very large features. So when you actually, in terms of actual size, the width of the auroral oval is probably about 1,000 miles, 100 miles. Well, that's for the EO. The EO spot is about 80 miles, something like that across. And for the whole width of the auroral oval is probably more like 1,000, maybe
Well,
800 miles.
It's very
something like that.
variable, and
it's
sometimes
variable,
you'll see some very narrow strands, and I
Yeah.
think the narrow strand here is probably on the order of 100 kilometers or
Yeah.
80 miles or so.
Right.
But it varies in time, and it sometimes occupies a much greater expanse across the planet.
So the importance of this particular picture, which we've only just seen glimpses of, it's just come in, is really important about showing that business that I mentioned, the variability of the aurora and the fact that the aurora is very structured. And so that sort of cartoon on the left, which is what a lot of images are that we have, much more blurry, much more spread out, is really the result of very small scale alternating currents, alternating features that are very temporal and spatially variable. And this glimpse that we have here shows that fine structure.
Harvey Lyford, freelance. I see nice longitudinal lines on that map, and I'm curious about how you determine a 0 degree of longitude, a Greenwich meridian for Jupiter, given that it rotates very fast and different parts rotate at different
Right. So Jupiter is a gas planet. So we don't have a mountain or any landmark that we can use to determine a 0 longitude. So there's no London on Jupiter. But we have received radio emissions from Jupiter going way back to 1955. And those radio emissions emitted in concert with the magnetic field are periodic. And so over many decades, we measure the periodicity of the radio emissions, and we assign the rotation rate of the planet to that periodicity. Now, some of the features you see on the planet, they move left and right in that coordinate system called zonal winds. And the Great Red Spot, for example, drifts in time, and that's why we're having a bit of a tough time targeting it with one of our flyovers. But that's basically, for any gas planet, how you have to determine the 0 longitude.
Yes, so this picture on the right, the movie there of the synchrotron emission, you can see that wobbling. So we've been measuring this since the 50s, and so we have a very, very accurate, I think it's 6 significant figures or something, measurement of the rotation speed of Jupiter. It's very accurate.
Oh, back to the other image. I hate to get onto the sense of scale thing, but one of the other things that was down in the lower right there that could provide a sense of scale is that dot of lightning flash. Do you guys have a sense of how big that is? And then that would help me kind of scale bar and decoder ring the rest of the image.
Yeah, that dot is about 100 kilometers in width.
Okay.
Mm-hmm.
Are there any other questions from reporters in the room?
Hi, I'm Ivan Amato with AAAS, and a great update on Juno, thanks. It's also, looking at a lot of the images you flashed, it's sort of a color fest, Jupiter, you know. So we've got the great red dot, these barges, brown barges, and then the blue, I guess in the southern part. Can you attribute those colors respectively to physics, you know, the particles and aerosols, versus chemistry?
That's actually a tough question. There's some theories that, or concepts that the bluish tinge in the polar regions would be the nature of the aerosols. The actual colors of the clouds is not well known, not well understood. It's various chemical compounds of sulfur and ammonia, and the chemistry is really not well understood. There's some theories about, you know, the longer some materials exposed to the radiation, the more color centers form, and so on. Realistically, this is false color. This is enhanced color. Jupiter would not look like that. It's more pastel, it's more yellows. If you're looking at it through a telescope, of course, it doesn't look anything like this. But one of the really wonderful things about working with the community of artists that we've been working with is that you see more when you enhance the color. So if I showed you this image in what it looks like for Jupiter in real life, it would be very pale. All the features would be there, but it wouldn't be very noticeable to our eye-brain combo. And I can tell you as a scientist that people do things with our data I would never do. But they have given me a whole new picture of what Jupiter looks like, and I'm so grateful to the art community for doing that. They've really stretched my own perception of what Jupiter looks like.
Do we have any questions on the chat? Are there any other questions from reporters in the room? No? Okay, great. That concludes our press conference. Thank you very much.
Thank you.